Now let's look at this concept of Monte Carlo methods, which primarily plays a very important role when we talk about simulations. Right? There are see a lot of applications in risk management kind of a space where we may have to simulate the data based on certain parameters. It's like a reverse generation of the data, right? Probably from the data, finding out the parameters like average, standard deviation is one aspect. Probably the reversal from the standard deviation and the mean, generating the original data is what is the process that is involved with your simulation kind of a process. Now, how do you generate it? There are various methods. There is a historical simulation, there is a Monte Carlo simulation. There are different methods in which you can generate the data or you can do the calculation. So Monte Carlo is one aspect where we talk about in terms of understanding the underlying distribution or the shape of the data, and based on the shape trying to generate the values, right? So when we look at this Monte Carlo, especially in case of risk management or in case of finance, we use it in areas like portfolio management. We use it very heavily in calculation of value at risk, which is one of the base for risk management. We also use it for option pricing strategies, option determining the option price. There are so many methods to find out the option price, but one such method is again using the simulation itself. But okay, from an exam standpoint, we are slightly relieved here. For the reason, these are primarily done through systems. So from a pen and paper perspective, it's much difficult to perform these kind of simulations. So whatever that could be asked from an exam standpoint is the concept that drives this process of simulation rather than the actual values itself, actual calculations itself. Now, how do we look at this? See, the first thing is, let's say my intention is to predict the price for the next 10 days for whatever reason. Probably I want to find out if I am investing 1000 today, what is the chance that I can lose more than 50 rupees after 10 days, right? For various reasons. Today, in this particular stock, let's say Dr. Reddy's, I want to invest 1000 rupees or 10,000 bucks. Now, I want to know what is the probability that after 10 days, my loss would be more than some 100 bucks from that standpoint. Or let's say I have some options, derivatives expiring on Dr. Reddy's after 10 days. In 10 days, there are options that are expiring. So if I want to purchase that option today, how much premium I should pay for it? These kind of scenarios can come out much better if I can do the prediction of the stock prices for the next 10 days. Right? If I can do the prediction of the stock price for the next 10 days. Now, on what basis I can do a prediction of the stock price? For that, I am simulating a price path. What could be the price for the next 10 days? Based on some of the patterns in the last couple of days or last few months or something, based on the patterns in the last few months, I would be generating a price path for the next 10 days. Now, we cannot give one single path because we cannot give an accuracy to the prediction. So, we will come out with multiple paths. And this multiple paths when they are generated using a particular kind of a concept and a distribution, there is a name that is associated for each of them. So the one such kind of a distribution that I can associate is what I call as a geometric Brownian motion. It's a very important aspect in terms of the stock price or any price prediction kind of a model. We assume that the prices will follow what is called as a geometric Brownian motion. And the interesting aspect of geometric Brownian motion is something like this. The change in price, DST, is nothing but generally the word small d is used for a change. This is the calculus usage of this. So what it says is the change in the stock price, DST, a small change in the stock price, it can be modeled using two components. There is an average change, right? There is a trend. There is a trend part which is nothing but the average, and there is some fluctuation part. Now probably just to showcase that scenario for you, let's say if I have been observing the last 1 month prices, 1 year prices of Dr. Reddy's, right? If I just do a simple plot of these with the dates, if I'm doing a simple plot, what we are saying, this is a kind of a plot that is coming up. On this graph, let's say if I'm trying to draw one line, a trend line kind of stuff, if I'm simply trying to draw, now you see there is some uppish movement that is being seen through this line. What it is saying, the price for each of the periods, when I have to predict the price for the next few periods, there is some constant growth part that is there, which is like a trend, and some random part around that trend. Right? This line, if we see here, this line is a kind of a continuously growing kind of a path. And the blue ones, which are slightly above in some cases, slightly below in some cases, they are signifying the random part. Right? So if I have to model a change from today to tomorrow, what this GBM tells me is the change is because of two parts. Because there is, from today to tomorrow, the straight line also goes slightly up. So there is a constant drift. The word associated with that constant growth is it called as drift. There is a constant drift along with a random part. So if I have to predict the tomorrow's price, we are talking about these two aspects. The constant drift that is coming up and a random component around that stock price is what is coming out. Now that is what this model is telling. There is an average. Mu t is nothing but the average of the stock price. There is some growth. There is some change around that average line, along with some component which is random, which is revolving around that the price based on the variance that is associated with it. If the variance is high, if the fluctuation in the stock price is high, even the random part could be higher. If the variance is lower, even the random part could be lower. So that kind, if at all you see any entity that is following such kind of a pattern, completely growing up or going down or even flatter, more not in terms of flatter, but generally for slightly going up or slightly going down kind of scenarios in a long run. But within that, some kind of patterns are there, some kind of randomness is there. For all those kind of entities, we can think of using a geometric Brownian motion for the modeling of them. So that's where he says you can use them generally for stock prices and exchange rates, because both of them you see some kind of a long term pattern in those kind of scenarios. But when we look at interest rates, we see a kind of mean reverting nature in them. Today if the interest rates are up, tomorrow they have to come down, right? And once they have come down, probably they may go even more down. So they actually fluctuate around a particular value, but they will not keep going up and up and up forever. Whereas the exchange rates or probably the stock prices or these kind of stuff, if you assume that they keep going in one direction, they show some kind of a trend always. In those cases, you can use the geometric Brownian motion to model them, because geometric Brownian motion takes these two components for describing a change. There is a constant change which keeps going up or down. There is a constant part which is what is associated with time, right? As for the next 5 days, there is some constant growth. So constant part which is more dependent on time, and there is a random part which is more dependent on the variance. And in the calculus world, dz, z is a normal random variable. dz is treated as a random variable. Wherever you use the word dz in a calculus standpoint, or probably not calculus, it's called stochastic calculus. In a stochastic calculus scenario, wherever we see dt, it means change with respect to time. When we see dz, it's a random part, right? So in this, if you can see, there is a stable part, there is a constant part with respect to time, which is based on the average, and there is a random part with respect to the standard deviation or the variance, where there is a dz that is associated. This equation is what is associated with a geometric Brownian motion. Now using this geometric Brownian motion, if at all I have to do the prediction, I can go with this kind of an equation. If I have to predict the stock price, actually this comes from the differential equation. Solving that differential equation, I get this kind of a scenario. Which one? This one. This is the random part. dz is there, right? dz is their random part, and based on the standard deviation that is associated, sigma is the standard deviation. So the increase, any change, we are saying two parts. One is a constant drift coming by the mean, average, and one is a movement around the average given by the standard deviation and the random part. Because we are saying it may go up or it may go down. It's random. It may either go up or go down. It is random. So I am modeling it to that dz. Now solving this equation, solving this differential equation, what comes out to me is, if at all I want to find out the change for tomorrow, I will take the stock price of today, multiply it with mu times the delta. Mu is the mean. I take the mean, multiply it with delta t. Delta t is per day. For how many days? Let's say I want it for 10 days. I multiply it as 10. Multiply it with 10. And similarly, I generate a random variable. That epsilon is nothing but the random variable. So I'll take the standard deviation. I take the epsilon, which is a random variable. I multiply it with root delta t. And that's how I generate the price for tomorrow. Now I'll just showcase in this Excel example. In this spreadsheet, what I will do is, let's say I want to generate the price for Dr. Reddy's for the next 10 days. Right? I want to generate the prices of Dr. Reddy's for the next 10 days. What I can simply do, First thing I will find out a few parameters. I'll find out the returns first of all. I'll take the returns. Here I'll take continuously compounded kind of returns. So how do I get the continuously compounded kind of returns? I'll take the logarithm. Log S1 by S0. Log today's price by yesterday's price. So I'll take log this by this. So this is a continuously compounded daily return. On a day base, so probably you could very well do this minus this divided by this. Right? Today's price minus yesterday's price by yesterday's price. But that gives me a discrete return. But if I take it as a continuous return, the same thing gets translated as logarithm of S1 by S0. So if I am saying this is the return, so for all the days, these are the daily returns. Now based on this, I can find out what is the average return. Right? So I'll say the mean return, mean daily return. The mean daily return on this data is something this much. That's the average daily return for me. And the standard deviation also I require in the modeling process. So I'll take the standard deviation of the daily returns. The standard deviation of the daily returns for me is around this much. Now, one thing we observe in this very small data, you will always find mean very less compared to the standard deviation. Of course, this concept we will use in our next chapter when we talk about volatility estimation. But just giving you a general observation, in most of these cases, especially when we deal with very small time periods, here the time period is 1 day, daily data. Whenever we deal with very small time period, we generally observe that the mean is much smaller compared to its standard deviation altogether. Alright, keeping that aside for time being. So I have the mean and the standard deviation. Now, what is the today's latest price? The latest price is 2238. Now, if I have to model for tomorrow, the next price, what is that it is saying? The components are the today's price into mu. Mu is already computed, the mean return. Number of days, because I want only for next day, 1 day, because I want to do for the next 10 days like that. So daily price, so I'll take delta T as 1. For 1 day I require, because mu is also daily, you have to match. Mu is a daily return in our example. So even T should be in terms of number of days. So anyhow I want daily return only, tomorrow's price only I want. So I can take delta T as 1. The same way sigma I already have, standard deviation. Root delta T is also 1 because T is 1 only. For tomorrow only I am going to do the prediction. Now this epsilon is a random number between 0 to 1. Epsilon is a random number between 0 to 1. Now what I will do? I will simply generate some random number between 0 to 1. Right? I'll generate a random number. It's a completely random. So there is this random numbers are something that are very heavily used in the simulation process. You generate in random. Each value has equal chance of occurring, and that too it comes on a very random basis. So like that, let's say I have generated some 1000 such random numbers, which means there are 1000 different paths which I am thinking of. I have generated 1000 such random numbers. Now what we are saying is, if these are the 1000 random numbers which I have, they are all random, right? So I keep refreshing, I get different set altogether. They are all random for me, and that's the reason to derive some kind of a conclusion, I always work on very large data sets. So that's where here I am going with 1000 or probably 10,000 is also worth enough. We'll see the problems and the benefits and the disadvantages of that kind of scenario. But the first thing is I have generated the random numbers. Now once I have them, I can predict the price path. Now what are the prices possible now? ST. So ST minus 1, the last day's price is this much, into mean, this is the mean, plus standard deviation into the random value, into root 1. Root 1 anyhow is 1 itself. So what it is giving to me, 30 is the change. Or probably for sake of doing this calculation, what I'll do is I'll keep these numbers as constants so that they don't keep changing for me. Once I have generated the random numbers, I'll keep them as constant. So these are the numbers and this is the change. So if you see here, these are the possible changes. Delta, if you see the calculation, delta ST is equal to this value. So now I can find out ST for that previous day's value. For this previous day's value, I'll add up this delta. So what is coming out for me? Different possibilities are coming up for tomorrow. Different possibilities are coming up for tomorrow. The same logic I can do for 10 days. I have 1,000 such possibilities. Now we will not take any one single value here. This gives me a distribution pattern. What is the chance of losing in one day? Right? What is the chance of losing? Probably more than 50 bucks in one single day. For those kind of things I will require. See, if I want the average, why should I do all this entire process? I know the average value there itself. 95% intervals we can build. So, and we can find out, okay, what are those 5% or what is that worst case? Right? Probably in this, what is the minimum most value? That's where we work with large possible numbers. Okay, what is the minimum most possible value here? 2241. 2241 is the minimum most, which means what is my loss? 2238. 2241. No, standard deviation. Okay, mean was constantly growing. Okay, this is not a return. Okay, the mean was constantly growing, and to some extent, so what it is saying is the increase is a very small increase of 3, which means it is lesser than the average increase. It is lesser than the average increase. If that average itself has been around 0, you could very well notice the other sides also. And one more thing that is being suggested in all these kind of moves is, now I can predict a price path like this. This is the delta. Sometimes people also use a slightly different mechanism. Based on the standard deviation, based on the mean, they generate a distribution. Let's say a normal distribution. For the returns, instead of directly taking just one random value and a standard deviation, they'll say the standard the particular data will follow a normal distribution, which means there could be a negative value possible, there could be a positive values possible. So they say that the values, the returns will follow a kind of normal distribution, And okay, now the same logic. I know that this is the mean. Now you see, I know this is the mean. This is the standard deviation. What I can do, I will expose these two things to a normal distribution to get to the returns. So how do I expose them? Let's say these are my random numbers. So this random number, because it lies between 0 and 1, I will map this value to the area of a normal distribution. Area of a normal distribution curve is 1, right? So when I say a normal distribution curve, area is equal to 1. Now the first random number 0.92. It may come somewhere towards the right? Corresponding to that, I can find out the Z value, which is the corresponding number of standard deviations away from the mean. I can find out that Z value, right, which will give me the number of standard deviations away from the mean. And what does that mean is, whatever the standard deviations away from the mean, I will multiply those many standard deviations and arrive at the return for tomorrow. Now, just as an example, if I have to use these random numbers only to arrive at the returns, the possible returns for tomorrow, instead of possible prices for tomorrow, I can arrive at possible returns for tomorrow. What is that I am doing there? I am taking the mean and the standard deviation which I got for this distribution, and I am mapping them to a normal distribution. So I can use something like, I'll use let's say one formula called norm inverse, where it requires the probability, the mean and the standard deviation. The probability, I'll map it to the random number. Probability, I will map it to the random number. Or probably we have already generated the random numbers. So probability, I'll map it to the random number. And the mean, I will take this value. The standard deviation, I'll take this value. So what comes out of this? What comes out of this for us? It says that the return is going to be 0.02 here. 2% return is what is going to come out. Now what I can very well do here. So in this case, there are some negative returns. There are some positive returns that have come out. Now what will I do? So this is the return for tomorrow, possible return for tomorrow. So what will I do? I'll take the today's price. I'll take the today's price, multiply it with that return. Or probably because we have taken them as continuous return, I'll multiply it with e power r. Because continuous return is what I have to multiply it with, not the discrete return. If I am multiplying with discrete return, I'll multiply it with 1 plus r. 1 plus 2, 1.02%, 1.02 is what I'll multiply. Because if this is a continuous return, I'll multiply with e power r. So I'll take it as e power r is nothing but this number that got generated. So I'm saying tomorrow's price through this model are these things. So now I can find out the minimum value through this model. What is my minimum value through this model? 2149. Right? 2149 is the minimum value. And 2238 is the today's. So what is it? I can lose almost 90 bucks in one single day. The worst case loss for me is around 90 bucks on share. But what is the chance of that? The chance of occurrence of that is 1 out of 1000. Because out of the 1000 scenarios which we have generated, one of them is having one of them out of that 1,000 is having a 90 kind of a loss. So probably that is where people work out. Okay, what is the chance of losing more than 50? Losing more than 50 means how much? 2238. 50 means 2188. How many of them are less than 2188? Correct? So I'll find out how many of them are less than 2188. Okay, 31 out of the 1,000 are less than 2188. So what is the conclusion I am making? There is a 3% chance, 31 out of 1,000. There is a 3% chance or 3.1% chance that your per day loss can be more than 50 bucks. This is what is the conclusion which I want to make using this simulation. I don't want any averages here because they are already available with the data. I want the actual distribution of the data for the future using this kind of geometric Brownian motion kind of scenario, wherein I am mapping it to a distribution. I am taking a random values. So like the same thing probably. Okay, now let me extend it a little bit more for you, wherein instead of one single value here, I'll take a random. I'll generate for 10 days like this, right? I'll generate for 10 days. So these are the random numbers for 1 day. 3, 6, 7, 8, 9, let's say 10 days. These are the random numbers that are generated for 10 days, or I think 11 days, I suppose. No, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, I'll remove this. So these are the random numbers that are generated for 10 days. Now what is that I can do? I can find out whatever, whatever is the today's price, right? Whatever is the today's price into e power r, each of them, if I do e power r, that is what I am going to get. So it's as good as e power the sum of all these things. That is the price at the end of the 10th day, right? The total price at the end of the 10th day, if I want to find out the simulated prices, on each day I am making a random move. Here I am not taking one single random number for all the days. For each day I am making a separate move. That is very much possible, right? So every day the movement could be random. So on each day I am taking a random move. So based on this, let's say at the end of the 10 days, what is it? This is the price multiplied by e power the summation of all these 10. So at the end of 10 days, these are your possible security prices. Now I can use it for any kind of an application. What is my worst case loss? At the end of 10th day, what is my worst case loss? 2003. So which means there is a chance that my loss is close to 235 bucks within 10 days. There is a small chance, 1 by 1000 chance, or 0.01% or 0.1% chance that my loss will be more than 235 bucks. The loss will be 235 bucks on one single share. Similarly, on the profitability side also I can look at the maximum. If I see, it is going to 2543. So which means there is a almost 300 plus, right? There is a 1%, there is a 0.1% chance that my gain could be 300 plus on one single day or after 10 days. In 10 days, my gain could be even 300 bucks, but the chance is only 0.1%. Now that is where people play around, right? In the risk management application, especially the calculation of value at risk. It is nothing but the definition of value at risk goes like, what is that loss amount with 90, tell me with 95% confidence or 99% confidence, what your maximum loss could be. Tell me with 95% confidence, what your maximum loss could be. Which means there is a 5% chance that your loss could be above that. You define some number for me, right? That's what we typically call as value at risk. That particular amount, which I can say with 95% confidence or 99% confidence, that my loss will not be more than that. So the other way of putting, there is only a 5% chance or there is only a 1% chance that the value falls below this. So let's say if I want from this, let's say I want, what is the 1% value at risk for 10 days, which means that particular number for which there is only a 1% chance that the value can go below that. Which means in this, because I have 1000 observations, I can take the 10th value, 10th smallest value. If I take those 10 small values, whatever is the boundary, if I define that boundary, there are 10 values which are below it and 99 percentile of the values are above it. That particular value is what I call as the value at risk, which will divide my total data, where 1% will be towards the left of it, towards the loss side, remaining 99% of the data will be towards the right side. So 1 percentile of the data or 5 percentile of the data kind. So here, if I take the 10th smallest number, in this I take the 10th smallest number, it is 2039. The smallest is 2005. The 10th smallest is 2040. So which means I am very much, there is only a 1% chance. There is only a 1% chance that my loss can be more than 200 bucks. 2238 today's price. After 10 days, the more than 99%. I mean, out of the 1000 values, only 10 of them are below this number, right? Which means there is only a 1% chance that my loss could be more than 200 bucks. That is how people compute the value at risk. Here, without using any formulas or anything, just by doing a simulation, I am able to find out the value at risk. The same logic people use for pricing of the options also. Now, assume that these are the 1000 prices that can come out after the 10th day. And probably I'll discuss it again in the options case, but just if you understand it. So if I say that there is some option that is set for a price of 2200, right? And because of the various paths you have generated, you know that on the 10th day, any of these prices are possible. So if any of these prices are possible, you will know whether the option will be exercised or it will be expired on each of the scenarios. If it is exercised, what is the profit? If it is expired, zero. The profit is the payoff is zero if it is expired. Otherwise, it is exercised. The difference is the profit. Take the average of them. That we can say as the price of the option. Without otherwise, there are traditionally so many other models called a binomial tree model or a Black-Scholes model used for pricing of the options. But this is a more what you call uh, unbiased to any unbiased to any kind of a pattern in the data, right? And even for complex kind of options, this model can be used. The formula based models, binomial trees and Black-Scholes, they have so many limitations and assumptions. Whereas here, any kind of thing can be simulated and you can use. That's one of the prime reasons people use this simulation mechanism as a very powerful tool in risk management, not to find out any average behaviors, but to find primarily the extreme behaviors. Just like I was saying, what is the minimum most value? Or probably what are the minimum 10%, 1% of the values? That is what, unless I have all possible combinations generated, I cannot get into those extreme understandings. That is where people use the simulation to generate those kind of numbers. So that's where VAR and all can be computed. Now, just to understand some of the mechanisms, so we have done to some extent the calculations and all, but conceptually, the terms wise, to generate random numbers or random data, we use two mechanisms. One is the inverse transform method, two is the bootstrapping method, to just generate the samples in a random manner. Bootstrapping is very simple. Probably I have taken the last 1 year data. What it says is, out of those 1 year returns, just pick up some 100 data at random. From the existing returns, let's say these are my existing returns. From the existing historical data, instead of taking the entire data, on a random basis, take out some 50 or 100 sample. And on that, do the mean, standard deviation, everything. Right now, we have done it on the whole data. But when I am using the process of bootstrapping, it's like from the total population, this is the total population if I say, from the total population, pull out a sample in a random manner. Right? So, we can when I pull out, it is as reflective of what has happened in the last 1 year. No other scenarios can be depicted. It's like a historical simulation procedure. You are not bothered about the distribution, nothing. From whatever the past data that is there, you are just pulling out the data from there, and based on that you are doing your calculation. Draw a random returns, random sample from the population data, and after that do the same process. But it is more of a realistic view because it represents what has actually happened in the last year. More of a realistic. But the problem comes if the samples are not independent. In this case, probably what we generally see, again, there is a technical analysis on one side which says the prices move in trends. Right? If the price is going up, probably for few days, there is going to be an uppish itself. If that is the case, there is some level of dependency with respect to the previous value. So, because of that, it is actually considered as a dependent sample. In this examples, generally the samples are considered dependent, not fully independent. So, in that case, bootstrapping method may have some limitations in terms of the usage. So, it's better that I resort more to the inverse transform kind of a method itself. What does this inverse transform say? Is just what we have done. Generate random numbers. Generate random numbers. So, in our example, we have generated 1000 such random numbers. Right? Generate the random numbers between 0 and 1. map them to the area of any probability distribution, because probability distribution, the area is always equal to 1. The area under that probability distribution curve always is equal to 1, or lies between 0 and 1. Even the random numbers are lying between 0 and 1. So whatever the distribution you want to generate, you map that random number to that probability distribution, area of the probability distribution. Correspondingly, you pull out the value. That particular process where you are generating a random number, mapping it to a particular probability distribution, and generating the actual values through that process, through a random number plus the distribution, generate the original value. That process is called as the inverse transform kind of a process. You are generating the numbers, generating the sample through two processes. One is a bootstrapping, wherein original from the existing data itself you are pulling out some sample in a random way. Whereas the second, the inverse transform kind of a method, you need the distribution of the data, generate a random number, map the random number to the area under that distribution, from there generate the original value, just like the way we have done in generating the stock prices, right? And after that, do either your value at risk calculation or option pricing. A lot of things can be done once that simulation is done. Geometric Brownian motion says the change in the stock price follows this kind of a pattern, right? So the inverse transform method is the way to generate random number. It need not be only for stock price. Anything where I use a random number and map it to a distribution, right? It's a very generic word. Geometric Brownian motion is a pattern that is used for stock prices and exchange rate modeling, right? But when I am saying inverse transform method, very simple. You generate some random numbers, right? I don't even know whether they are stock prices in this case. I generate a random number, map it to a probability distribution. In this case, we have mapped it to normal distribution. Probably I can map it to t distribution. I can map it to chi-square. I can map it to any distribution of my choice. Because any distribution, the area is equal to 1. Probability lies only between 0 and 1. Right? Binomial distribution, Poisson distribution, I can think of any distribution. They all lie between 0 and 1 only. So I can map the random number with that distribution and use it to regenerate the value. That process is called as the inverse transform method. Whether I use it for stock price modeling, exchange rate modeling, or anything else. Right? Simply speaking, let's say I want to generate the heights of the people. I'll use inverse transform method. I'll say, let's say the average, I know the average height is 165 centimeters. And let's say the standard deviation in the heights is 15 centimeters. Just with these two, and I know that it is a normal distribution. If I know these three pieces, I'll generate the heights of hundreds of people. I'll generate the heights of hundreds of people as if I have gone to them and measured their heights. As if I have gone to them and measured their heights, right? Probably if I generate a huge value, you will see, let's say these many I have generated. It means that, okay, I have taken really gone to many people and actually measured their heights. Now you look at, just try to calculate it back, average. You try to calculate the average, 165. What we have started the assumption with. You try to calculate the standard deviation. What you have started out with, right? And this is also normal also. The way to check out the normal distribution is I will try to compute the skewness. Skewness, if it is 0, it's a normal distribution. It is 0. So it looks as if I have gone to 5,000 people, measured each one of their heights explicitly. So what did we do here? We know only two information. The average height is this much. The standard deviation in the heights is this much. Based on some previous study or whatever, we came to know that these are the two and it follows a normal distribution. Now what did we do? Using inverse transform method, we generated random numbers, mapped that random number to a normal distribution, based on that generated the values. Now this values will definitely follow a normal distribution, whereas the random numbers originally generated, they follow a uniform distribution because they are uniform. Any value can come. There is an equal chance of all those random numbers coming up. So they will follow random numbers originally generated 0 to 1. They will follow an uniform distribution. But I have mapped that to normal distribution. So now the new generated values, they are following a normal distribution. Only this process we call it as the inverse transform method. So I may use it to measure the heights. Right? On this heights also I may make some statements. What proportion of the people will have height less than 140 centimeters? Right? What proportion of the people will be more than 200 centimeters? If I have to make those kind of statements, I can easily make, because I have generated a big set of sample which is following the same distribution as I started off with. So it helps me in doing these kind of extreme analysis or breakdown at every chunk, not just the average and the standard deviation, but at each interval, it can help me in trying to come out with the details. Right? So it can be used for all these kind of applications, right? Because it helps us in simulating the price path quite comfortably. So anything that is associated with the future forecasts or applies on the future price movement, whether it is option pricing or the determination of value at risk or any other scenarios, it can definitely help me in doing the modeling for them. Even if there are non-linear payoffs, typically options are an example of non-linear payoff. Right? Simple reason being, I can back out. So it's not a uniform profit and loss scenario. So even for complex instruments, we'll see slightly later also, not just for simple options and all, even for extraordinary complex applications, as long as I can identify a distribution associated with them, I can use this simulation to generate the price path. From there, I can do whatever I want. Right? It gives me so many scenarios for the price for the next 10 days later. So all these possibilities are there. Now you can think of what is the chance it will be more than this, what is the chance it will be between this and this. Even the probability generation becomes very easy once you follow that kind of a path. Sometimes in our numericals he gives, right, there is a 20% chance of getting 15% return, there is a 30% chance of getting 12% return. In reality, it can be generated through that kind of a mechanism. Right? Then, the biggest drawback is, if the distribution is not clear, right, because the entire generation is based on the distribution. So if the distribution is not clear, the generation has a problem. 1. 2, this is again, we'll discuss about this in options also. This kind of a model can be used only if options or any of these complex instruments, they go until maturity. In middle, if I am actually getting out of them or selling them off or exiting out of those kind of contracts, they have some difficulty in doing the predictions. Of course, you can still do it, but it's a very tedious process at those kind of stages, right? And today, probably based again for a risk manager's standpoint, there is a very heavy trading that is going on Vega. We call it as Vega trading, which is nothing but trading based on volatilities. The buying and selling purely based on volatility, not price going up, price going down. Right? In options, we'll also see there are some option trading strategies which are heavily targeted towards volatilities. There is something called a straddle strategy. There is something called a butterfly strategy. These are all more targeted towards the volatilities. So any trading, any buying and selling I'm doing to address the volatility aspect based on the volatility. Sometimes the most common trading is price goes down, I buy, price goes up, I sell. That's a very common trading strategy. Today, the trading strategies are moving more and more towards the volatility based trading. Vega trading. Again, powerful quantitative models and all are coming in those kind of aspects, where the trading is probably purchase low risk securities, sell high risk securities. So the trading is purely based on that kind of standard deviations and the volatilities. That kind of trading is called volatility trading. So it can even help me in assessing the risks that are associated with the fluctuations of the security prices also. So like that, once you do a simulation, the kind of benefits you can derive out of it are phenomenal in nature. Now, in all this, whatever we have done, some of the things that come to the problem is speed versus accuracy. Now we have gone with only one variable, one security for 10 days. So many random variables got generated. And we have simulated only 1000 outcomes. But with that 1000, there is a possibility that the accuracy may be slightly difficult. Probably if I generate 10,000 or 1 lakh, if I generate more and more such kind of simulation runs, accuracy can be very high. Because the whole picture can be painted very comfortably. All possible random numbers can be taken up. So the higher the number of simulation runs I am doing, the better is the accuracy I will be meeting with. But imagine if I have 10 different securities to create a portfolio. Right, here we have taken only one security for 10 days. Now I have 10 different securities to create a portfolio. The headache is, okay, I can do the modeling for the prices for all the 10. But when I am talking of a portfolio, it's just not the prices for the 10 days. Even their correlations can keep changing over the period. Right? Today the correlation could be 0.6, but tomorrow it could be 0.57 or 0.54. Even they keep changing over the period, which means the number of outputs which I have to generate is extremely large. Because correlation is always between a pair of securities. Now if I have 10 securities, probably I have 45 such correlations I have to prepare for 10 days. So 450 such columns of data I have to generate. 450 columns of data for 10 days, correlations, then prices. It's a huge computational model. And because of that, speed gets very badly affected. Probably the same example, if I replicate it with 25,000 records instead of 1000, if I do it with 25,000 records, you'll see Excel gets stuck for me. 25 or 50,000 records, if I do it, probably there is a hanging that happens in Excel. So that is what we are typically talking about, the compromise between speed and accuracy. Of course, the more and more I generate, The error part is, see, in any sampling also we were saying the higher the sample size, there is a good chance that the sample mean will be equal to the population mean, or the error will be much minimal. The same logic here. The more the number of simulations I am generating, there is a higher chance that the error will be more and more minimal. But the scenario will become more and more difficult if there are large number of assets, especially for portfolio management process. If I have to use that, if there are large number of assets or too much of complexity in the financial instrument I am doing a valuation on, or I am doing a modeling on, it becomes very tedious process. So that's where I have to look at a compromise between speed and accuracy. And so if I'm reducing the number of simulations, I have to compromise on accuracy. If I'm increasing, I have to compromise on speed. But the typical vote should always be to the accuracy itself. So probably even if my system is slightly, because both of them have a cost involved. See, in this case, I'm using this kind of a system where generation may be more or less quicker, but earlier people used to use more of a manual ways. Random numbers, there used to be random number tables. From that random number table, they used to write down the random numbers and based on that generate, which is a very tedious process. So to overcome those kind of things, sometimes to accelerate, they have given these kind of models. You just change the sign of the random variable. But again, the independency is lost. Let's say you got a return of 0.2% through one of the random variable which you have generated. It says you also take minus 0.2% as another scenario. So what happens here? It's as if it has generated another random number which is giving you a return of minus 0.2%. But in this case, the drawback for us is these two are actually linked. When you got a 0.2, you are sure that there is a minus 0.2 also in the data. So because of that, some compromise will come up, but in the huge set of data you are working off with, it's not, because anything which is on the positive side, you are also assuming that equally it may reflect on the negative side also for you. That is what is the intention behind asking you to, I mean, if you are having a system issue, even by doing these kind of stuff, instead of generating the same formula 10,000 times, you generate it only 5,000 times, change the sign and make it 10,000. So that way there is some acceleration that can happen and some kind of a time saving. And probably it's also saying that don't do the sampling across the table. Probably do a sampling only in the outlier. Selected sampling is what you can try doing to enhance the speed and accuracy kind of stuff. This is the another important aspect, especially when we are doing for portfolio. I was talking of the correlation and all, right? The correlation, if there are existing between two securities, right? Let's say I want to create a portfolio using these two. Now, if I want to do a price path, I can do it separately for this. I can do it separately for this. I can say this is following one random variable. This is following another random variable. If I do that, I am assuming that these two movements are completely independent. Am I right? I am assuming that these two movements are completely independent. That is what is the assumption I am going with. If I am definitely generating one random number for this, another random number for this, no interrelationship between the random numbers, I am simply going with an assumption that there is no correlation between Dr. Reddy's and HCL Tech. But in reality, there may be a correlation between Dr. Reddy's and HCL Tech. Let's see. You see, already system performance got slowed down. You see, it's taking some time to change the values. Now, if I am taking the correlation between correlation of the returns between Dr. Reddy's and HCL Tech, it is saying almost 0.08. Of course, this is giving me close to 0 itself. But for some securities, the correlation may be much higher also, right? So, how do I generate the random numbers? If at all, there is a correlation between the two securities. Especially for portfolio, that is very much needed for me. I cannot generate independent random numbers for both of them, right? Because they are not independently moving, there is some level of dependency between them. If this is up, probably even this also has to be up. Such kind of scenario is there. So that is where Cholesky factorization is what has actually come into scenario. Especially when I have correlation existing between the two random variables, two data. What it simply says is, okay, you generate some random numbers for the first one. You generate both the random numbers. I'll take only a few things because the system is already loaded. Let's say I generate, let's say some 25 random numbers here, and I'm generating another 25 like this. Using this, if I do a modeling, it's completely independent. Now what the Cholesky factorization says is, you identify the correlation between the two. Let me, by default, for clarity purpose, let me assume that this correlation is 0.8 instead of 0.08. Let me say that it is 0.8. What the Cholesky factorization says is, independently you generate two random numbers, two sets of random numbers. But when you are assigning something, what you do is, when you are assigning something for calculation purposes and all, you modify the random numbers. Whatever are generated, you modify them. How do I modify? Let me just freeze these things first. Let me just freeze these. So these are generated completely in random. Now what it says is, you generate two new random numbers where the first ones are the same. The first ones are the same as what they are generated. But the second one incorporate the correlation part. How do I incorporate the correlation part? You give the correlation weightage to the first one. So what it says, the first one when you are creating, you multiply this correlation, whatever was existing, with the first part, with this one. You multiply this correlation with the first one, which means you are bringing in some level of dependency with the first. The second random number, you are bringing some level of dependency with the first random number. So the correlation, you are multiplying it with the so generated random number, and some part you are leaving it to random. So what is that some part? I am taking the square root of 1 minus r squared. 1 minus r squared, whatever is this, which is nothing but, instead of taking, see, I am multiplying the correlation. I am multiplying the correlation with n1. Logically speaking, 1 minus correlation with another random number. I am multiplying the correlation with one random number. 1 minus correlation with the another random number. Instead of directly taking 1 minus correlation, all I am doing is square root of 1 minus correlation square. Instead of simply doing 1 minus correlation, we are doing a square root of 1 minus correlation square. We are doing a square root of this. Sorry? No, even the sign does not impact. Yeah, if the correlation had been minus 0.8, that impact will come up. So from that standpoint, we are doing a 1 minus r squared and taking the square root of that part. So this part, I am square root of 1 minus r squared, I am multiplying it with the second generated random. So what is happening in this process? There is a new random number that got generated for me. Now these are the new random numbers. So in some cases there is even greater than 1. In some cases, so because there is a dependency between the two, I am generating it through this process. And through this process, I can generate the values of the assets. So when I am doing the generation through this process, wherein the second random number for me is the correlation times the first random number plus 1 minus the correlation squared, square root of the 1 minus correlation squared times the second random number. So whatever are the newly generated random numbers, I will use them to generate the resulting value. They will bring out now the weightages of the first random number I'll apply to Dr. Reddy. The second I'll apply to HCL Tech instead of applying a random number on HCL Tech altogether. That will make sure that the correlation between those two securities is taken care of. The same logic can be extended to n number of variables, whatever have interdependencies between them, all of them between each pair, I will do this kind of an analysis and try to improvise. But in this, again, the problem is if the number of factors are very large, right, or not two securities, if I have 20 such securities, correlations are too many and the mapping becomes quite confusing. And if the correlations are changing heavily with time, as 5 days back the correlation was this much, today the correlations are something else, because here all we are doing is we are taking one correlation number and we did the entire exercise. But if the correlation keeps changing with time, even that is a big serious problem. Now in some cases people address especially the multiple assets scenario through a process called principal component analysis. Statisticians even call this process as factor analysis, which is nothing but using some statistical techniques, you can reduce the 20 factors into 3 or 4 most relevant factors. It's not eliminate, it's group. So even if there are 20 variables, you can group them into 3 or 4 variables. The logic being, probably in regression, there is one assumption. The independent variables should be really independent. They should not be interdependent, which is what we discussed as multicollinearity principle. The independent variables should be independent. If they are interdependent, what will I do? If there is a correlation that is existing between them, what will I do? If I drop one variable, data loss is occurring, right? That is where my principal component analysis comes into picture. Club the variables. Instead of dropping the variable, club the variables, whichever are having heavy correlation between them, club them and form overall, even if there are 5 variables, make them 2 variables. So that those 2 variables are completely independent. There is no correlation existing between those 2 variables. That is what is the typical output which a principal component analysis gives. Mostly all the statistical tools, SPSS, Minitab, SAS, any of these statistical tools, they generate this factor analysis or principal component analysis quite comfortably. Right? Manually, it's a very tedious task to remove the interdependencies between them. That's the reason a manual procedure always says drop the variable. But it's one of the very wrong things to do from a reality standpoint. So the principal component analysis is something which comes into the picture, where you have to club the variables, reduce even at 20 into 3 or 4. But those 3 or 4 are completely independent, which means their correlations are zero now. When I do this principal component analysis, what happens is, though the 20 variables are there, 20 assets are there, and there is a lot of interdependency between those 20 assets, once a factor analysis is done, that 20 will get reduced to 3 or 4. Nothing is eliminated here, I'm telling you. 20, they are formed into some linear combinations of these 3 or 4. Right? The 3 or 4, let's say probably I have A, B, C, D, E as my original securities. A new variables are created called XYZ. Probably where it would be like, okay, 0.8 A plus 2B minus C, something, some linear combination of the existing values will be created into X, will be created for Y, will be created for Z, and these XYZ literally will not have any kind of correlation between them. You try finding out the correlations between XYZ post the factor analysis, post the principal component analysis, you will find that the correlations don't exist between them at all, which means your task of making this Cholesky factorization and all, even that is eliminated. You just need to do an independent forecasting or independent price path creation for those 3 or 4 created variables. That will solve your entire purpose, because they are no more interdependent, they are completely independent. So in this simulation process, again, there is something called deterministic simulation and scenario based simulation. Scenario based simulation is what which we have discussed just now. I create a principal component analysis, reduce the number of factors to 2 or 3, so I can test different kinds of scenarios, worst case, best case, because hardly I have 2 or 3 factors and hardly any interdependence between them. So the simulation becomes more easy when I am doing a scenario based simulation. But when I am doing a deterministic simulation, all we are doing is, we are not selecting the sample on a random way. We are going on a determined way. So I am carefully selecting the samples, and because of that, probably my error can come down very fast. But at the same time, there are some other problems that can come out, bias that can come out, because my sample selection is not completely random in nature. So generally a scenario based simulation is what is more preferred than a deterministic, unless we are very much clear that these data points are really not required for our analysis. Even if they are added, they don't add any kind of a value to our analysis. Only when I am fully determined, I will only select some specific samples out of that data, not in a completely random fashion. So some of the limitations, as we discussed, this entire simulation can be applied for those data which show some kind of upward behavior or a downward behavior kind of stuff, not where they show a mean reverting kind of a behavior. So for mean reverting behaviors, which are like fixed income securities, majorly they go with a mean reverting behavior. So wherever the fixed income securities come to picture, we cannot use the geometric Brownian motion or a simulation kind of stuff like this. They have another forms of simulations to go with. They use random numbers still, right? But this kind of procedure, using the geometric Brownian motion and all, I cannot apply to the mean reverting kind of scenario. So that's where there are so many other models which are heavily developed for fixed income kind of securities, especially where there is a mean reverting kind of scenario coming into picture. There are so many others. So that's a completely separate world altogether. right? So from our Monte Carlo simulation standpoint, we just need to understand the limitation of the Monte Carlo simulation, which is the applicability to something where a path can clearly be observed, but cannot be applied to where the mean reverting kind of stuff, especially for fixed income securities. There are so many. Probably if you look at any good derivatives book today, right? Any good derivative, and probably even for your FRM, for the financial markets and products, the book that is prescribed is the derivatives by John C. Hull. The new versions of the new chapters that get added up into that book from edition to edition is purely on these areas itself. The interest rate based models are the newest chapters that keep get adding with the edition, which means that's almost like the new areas of research that are going on. So you have a Cox Ingersoll model, there is a Vasicek model, there is a Schwartz and Brennan kind of model. So each one have come out with their own mechanisms of predicting the interest rates. These are all for interest rate modeling, which will be used for, again, fixed income derivatives pricing. Fixed income, any evaluations on the fixed income, the key thing is interest rate forecasting, right? The interest rate forecasting is the core element which will price my fixed income products, right? Otherwise, there is nothing else which is variable. In a fixed income, the only variable is interest rate. So these all models, they are targeting on the various interest rates. How do you model the interest rates? Showing a mean revertibility behaviors, all these kind of stuff. Long term interest rate average versus short term fluctuations in the interest rates. They come up with all these kind of mechanisms. So I cannot directly apply this kind of geometric Brownian motion based simulation procedures for the interest rates. You can do these applications for stock prices, which we have just now done. The same kind of a logic you can use it even for the exchange rates or any others, which you see there would be a kind of a growth up, a growth kind of thing coming up, or a fall kind of thing coming up, not a determined reverting in the behavior kind of stuff. All right.